All right, good morning, everyone. So yeah, first of all, we released assignment 2 this morning. So we'll go through the spec, and then in the second half of the lecture, we'll talk about the last part of graphs, which is which is not ADTs, but minimum spanning trees. Okay, so yeah, let's talk about assignment 2. So the first thing is that it's due on Thursday of week 10. Okay, not Friday, because Friday is a public holiday, right? In both week 9 and week 10, Friday is a public holiday, which is unfortunate for everyone who has a tutorial on Friday. But we will schedule some replacement classes, all right, for week 9 and week 10, so that you can actually go to a tutorial and you can get your labs marked. Okay, so yeah, so it's due 8 p.m. Thursday, week 10. It's worth 15% of your final mark, just like with assignment 1. Okay, and late penalty is all the same. Okay, so first of all, there's a little backstory that you can read, but the setup is exactly the same. So you just download by clicking the link here or running the unzip command while you're connected to CSE. Okay, and yeah, the theme of the assignment is about maps, right, and navigation. So kind of like, how does your GPS find a route from where you are to where you're trying to get to? Okay, so here are the files you'll be given. So there are the make file, which we've been using to compile programs throughout the course. There's the roadmap ADT. So that's one part of the assignment that you'll be implementing. So there's the interface, which you're given and you shouldn't change. And there's the implementation, which you need to fill in. Okay, so here I've downloaded the starter version of the files. So I'm going to open up roadmap.c, or we'll open up roadmap.h first. But you see here that we have our typical type def for an ADT. We have a hash defined for the maximum number of roads per node. So with roadmaps, we have intersections and roads, right? So if we represent this as a graph, right, the vertices would be our intersections, and we just call them nodes because nodes is easier to say, and the edges would represent the roads. Okay, so max roads per node is the maximum number of roads that can be connected to a particular intersection or node. Okay, then we've got a road struct. Okay, so a road struct contains from and to. So where does the road start? Where does the road end? It contains travel minutes. So this is how long it takes to drive down that road from start to end. And we have a couple of fields here which are used in task 4. So I will elaborate on those later. Okay, so the roadmap ADT you're actually going to be working on throughout the assignment. So in all 4 tasks, there will be functions that you need to fill in the roadmap ADT. A lot of them are for task 1 and task 2, and just a few functions you need to implement for task 3 and task 4. Okay, so with task 1, there is the roadmap new function. So this shouldn't be a surprise, right? Every ADT function needs a function for creating an instance of the ADT. Okay, so roadmap new, and it takes in the number of nodes. Okay, and once you create the roadmap using this function, you can't add any more nodes to it. Okay. There's also a function to free the roadmap, a function to get the number of nodes, a function to get the number of roads. Okay, and in the roadmap, we can have one-way or two-way roads. Okay, and both of these count as a single road. So a two-way road doesn't count as two roads, it just counts as one road. So just be careful about that. Okay, next up we have a function to add a road. Okay, so we want to be able to add a road between two intersections. Okay, the road can be either one-way or two-way, and that's specified by this argument here is two-way. Okay, and when you create a road, you specify the number of minutes it takes to drive from start to end. Okay, and there are a couple of conditions for whether you can add the road or not. Okay, so first of all, if one of the intersections already has max roads per node roads connected to it, then you can't add the road. Okay, so the function returns a Boolean that tells you whether the road could be added or not. So if the road can't be added, then the function should return false. Otherwise, it should return true. Okay, and it's important here that this regardless of the direction of the roads, right? So you can't add a road if there are already this many roads connected to node 1 or node 2, and it's regardless of the direction of these roads. So if you have, let's say you want to add a road from A to B, right? And A already has 4 roads connected to it, right? Regardless of the direction. So maybe there are 4 roads going from other nodes to A, like one-way roads, or there are 4 two-way roads between A and 4 other nodes, then you can't add the new road, okay? And the next condition is that you can't add a road if there's already a road between the 2 nodes, okay? Okay, so I think that's all. Oh, there is an assumption here that you can assume that travel minutes is between 1 and minutes per day minus 1. Okay, so no road is going to take 1 full day or more to travel. Okay. Okay. Next, we have roadmap get roads from. Okay, so the purpose of this function is to get all of the outbound roads from a particular node. Okay, so by outbound, we mean all the roads that you can use to drive away from a particular node. So say you're at a node A, right, and you call get roads from for node A, right? These are all the roads connected to road A that you can use to drive away from road A. Okay, so these might be two-way roads that are connected to road A, or they might be one-way roads that start at A and lead somewhere else. Okay, so that's get roads from. And the way that these functions work, get roads from and get roads to, is that they take in a node, right? So that's the node that you want to get roads from or to. And it also takes in an array of roads. And this is where you actually store the roads, the result roads, okay? So yeah, when we want a function to return an array, right, there are kind of 2 ways we can do it, right? We can either have the function dynamically allocate an array, right, and then return that array, or we can pass in an array like a buffer, and then the function fills in the array, right? So we're doing it this way for this function, and the function returns the number of rows that were stored in the array. Okay, it's It's probably similar to your task 5 in lab 5, the get friend recommendations, right? So the way that function worked was you store the friends, the recommended friends in the array, which was passed into the function, and then the function returned the number of recommended friends. Okay, so that's get roads from. Get roads to is a similar idea, except you want to return the roads heading towards a particular node. Okay, so it stores the inbound roads to the given node. Okay, and both of these functions assume that the roads array is large enough to store all the roads that need to be stored. Okay, so that's the .h file, and I'll open up the .c file. Okay, so the .c file is what you're actually going to be writing your code in. So there's the struct roadmap. So you're going to be adding fields to this struct to implement your roadmap. And then here are all the functions that we just talked about. Okay, so roadmap new, free, num nodes, num roads, add road, get roads from, and get roads to. Okay, and let me see now if we go to the spec, is there anything in the description that isn't in the .h file? Yeah, okay, so there's also required time complexities. Okay, so when you implement these functions, you need to make sure that their time complexity is the same or better than what's specified here. So with roadmap new and roadmap free, there's no requirement. So the time complexity can be anything reasonable, right? So it shouldn't be something huge like on cubed, right? Or O of 2 to the n, because that would be way too slow. So just make sure it's something reasonable. On squared would be fine. On would be fine. Okay, and then you have these functions, num nodes, num roads, add road, roads from, and roads to. So the time complexity for these functions is O1, okay? So make sure you implement these functions in O1 time. Okay, let's see. Okay, so that should be it for the functions. And now for testing. So in order to test your ADT, we have a program called test roadmap.c. And in that file, our tests, our basic tests for each of the functions. Okay, so we have tests for each part. For part 1, we have 6 simple tests, 1.1, 1.2, 1.3, 1.4, 1.5, and 1.6. Okay, so you can have a read of this file. But the way you run tests for part 1 is you run the test roadmap function and you pass it the number 1, right? That's for task 1. And if we run it now, it's not going to pass the first test, right? It's not going to pass any of the tests. So it's going to stop at the function test11 because that's the first test. Okay, so the tests are assertion-based, which means they use assert. Right? In assignment 1, you would have seen us use assert for the counter ADT tests. Right, so what assert actually does is it checks a condition. Right? If the condition evaluates to false, then the program crashes. Okay. So if the program runs and it prints out all of the tests passed, so test 1.1 passed, test 1.2 passed, and so on, then you know that you've passed all the tests. Okay, so yeah, we recommend you to add more tests to this file because the tests that we give you are only basic tests. You can also run the tests using the autotest command. So we have an autotest script. And to run it, you just specify what part of the assignments you want to test. Okay, so autotest1 will test task 1, and it'll do the same thing as test roadmap 1. Okay. Okay. Cool. So that's it for task 1. Does anyone have any questions about that? Yep. So this is all about implementing the roadmap ADT. Okay, onwards to task 2. Okay, so task 1 was about road maps and adding roads. Right, so task 2 is about islands. So on the particular world that this assignment is set in, this particular planet, there are islands. Okay, and the idea with islands is that if two nodes are on different islands, then you can't drive between them, right? Then there's no road between them. So this might be similar to a concept that we've covered in lectures, hint, hint. But for example, this particular setup contains 3 islands, right? 1, 2, and 3. Notice that even though this is a one-way road between 0 and 5, right, and you can't actually drive from 5 back to 0, that still counts as one island here. Okay, so 0, 3, 5, that's one island. And here, this is also one island. And then this is also one island. Okay, and yeah, so the reason we want to process the islands is if in the later stage of the assignments, we have route navigation, right? So route calculation. So if you're trying to calculate a route between 2 nodes on different islands, then there's no route between them, right? So you want the algorithm to be able to easily detect that and just return that there's no route without, trying to actually find if there's a path from A to B. Okay, so yeah, so here we want to pre-process the nodes and the roads to identify islands. And the functions that you need to implement are also in the roadmap ADT. Okay, so first of all, there's a function called process islands. Okay, roadmap process islands. So the purpose of this function is to simply look at all the nodes and the roads in the map and store information about islands. Okay, so it doesn't actually do anything externally, right? It doesn't return anything. It doesn't take anything in except for the map. Right? All it does is calculates information about the islands and stores it so that you can implement the next bunch of functions. Okay, and there's no time complexity requirement for this function. So it's fine to implement it efficiently or reasonably inefficiently, but don't make it wildly inefficient like on to the 4 or exponential. Okay, so when this function is called, you can assume that no more roads are going to be added to the map, right? The problem is if you add more roads to the map, then the information calculated by this function might not be accurate anymore, because you might add a road between two islands, and then that would just become one island, and yeah. So you can assume that after this function is called, no more roads are going to be added. It says so here. Okay, so after this function has been called, we can now call these functions to get information about islands. Okay, so first of all, there's a function called num_islands to get the number of islands. Then there's a function on same island. So this function takes in two nodes, and it returns true if they're on the same island and false if they're not on the same island. Okay, so this function is useful if you're trying to calculate a route from A to B, right? If the two functions, if the two nodes are on different islands, then there's no point in calculating a route. Okay, next, there's set island name. Okay, so we want to be able to give our islands names. Okay, so the point of this function is it takes in a node and a name, and it says that the island that this node is on, we're now going to call it this name, okay? And the function can be called multiple times. If it gets called multiple times, then the name just gets replaced, okay? And then because there is a function to set an island name, there's also a function to get the island name. So this function takes in a node and should return the name of the island that this node is on. Okay, and if the island hasn't been named yet, so we haven't called set island name on one particular island and we try to get its name, then the function should return null. Okay. Okay, and here is an example. So suppose we have this particular road map, right? Clearly we have 3 islands. So after we call road map process islands, if we call num_islands, it should return 3. Right, if we check whether 0 and 3 are on the same island, it should return true. If we check if 0 and 5 are on the same island, it should return true as well. Same for 5 and 0. Okay, but 0 and 1 are on different islands, so the function should return false. Okay, and we have an example for a set island name. So if we set island name for node 0, right, and we want to set the name of the island to Bora Bora, then the name of this island, right, is now Bora Bora. So if I try to get the island name for node 0, 3, or 5, we should get back the name Bora Bora, okay? Okay. So I'll just quickly show you these functions in roadmap.h. Okay, so it's just process islands, num_islands, on same island, set island name, and get island name. Okay, and notice that the last 4 functions assumes that roadmap process islands has already been called. Okay, otherwise, I mean, the information about islands hasn't been calculated yet, so there's no point in calling the function. Okay, and here are the task 2 functions that you need to fill in. Okay, and testing task 2 is the same as testing task 1. You just run test roadmap and you pass it the number 2.
since this is task 2. Okay. And you can also test task 2 using auto test 2. Okay, so it does the same thing. The auto test script just gives you a nice interface to testing all the tasks. Okay, so any questions about task 2? Okay, so let's have a look at task 3. So task 3 is about navigation, about calculating routes. Okay, so in addition to the previous functions that you implemented, there's one more function that you need to implement in the roadmap ADT, or actually 2 more functions, but they're very related to each other. So there's functions about adding traffic lights and checking if a node has traffic lights. Okay, so yeah, so the roadmap, right? Nodes might have traffic lights, so these functions are for adding and checking whether a node has traffic lights. And the main point of this task is to calculate the shortest route between 2 nodes. Right? So you have to implement the navigate function. The navigate function takes in the starting node and the ending node. And it also takes in the departure time. Okay, so when do we start traveling? Okay, and there are a bunch of related structs. Okay, so first of all, there's the time struct, which takes in the hour and the minute. Okay, and then there is the route struct and the leg struct, which stores information about the route. Okay, so first of all, you have the route struct, which contains information about the entire route from start to finish. Okay, so you've got where the route starts, where the route ends. So these should end up being the same as the arguments that are passed into navigate. Okay, so you can just copy those in. There's also the start time of the route. So this will be the same as the time that you're given. And then there's the end time, which you're going to need to calculate. Okay. And then there is the total duration of the route. So how long does it actually take in total? And then there is a legs array, okay, which contains information about the legs of the route. Right, so every time you travel down one road, that's called a leg. Right, so if you travel down 3 roads, then the route will have 3 legs. Okay, and the leg struct contains information about these separate legs. Okay, so each leg will have a start node and a finish node. Okay, and each leg will also have a start time and an end time, and then the duration of the leg. Okay. Okay, so yeah. Okay, there's also the traffic light thing, which I haven't fully explained yet. So with the traffic lights, they affect how much time you have to wait at each node. Okay, so if a node has a traffic light, then you have to wait this many minutes before moving on to the next road. Okay. Keep in mind that the traffic light doesn't affect
the starting node and the end node. Okay, so if you start at a node that has traffic lights, then you don't actually need to wait. Okay, you can go straight away. And the destination, so if the destination has traffic lights, that doesn't matter. Okay, that doesn't affect the trip time. Okay, and here's an example. So suppose these three nodes have traffic lights, right? So the nodes with the dashed lines, and you're trying to get from 0 to 5. Okay, so the result should be this, this struct over here, or this set of structs. Okay, so this is the route struct, right? So it contains information about the entire route. So you can see that it starts at 12:45. It ends at 13:04. That means the total duration is 19 minutes. Okay, and the shortest route involves 3 roads. So this legs array is going to contain 3 leg structs. So here we have the 3 legs. So it turns out that the shortest route involves going from 0 to 1, then 1 to 2, then 2 to 5. Okay, and there are some notes here, so make sure to read those to get a better understanding. Okay. Cool, so that's task 3. And to test task 3, there are 2 parts to it. Okay, so first of all, there's the roadmap ADT. So remember, you need to add a couple of functions in the roadmap ADT to deal with traffic lights, add traffic lights, and has traffic lights. Okay, so these functions are really simple. So there is only one test for it in test roadmap.c. Okay, so I'll just show you the test. Okay, so first of all, we create a roadmap, right? Initially, the roadmap doesn't have any traffic lights. Okay, so none of the roads should have traffic lights, but then we add traffic lights to a few nodes, and then we just check whether these nodes have traffic lights. Okay. So the way you test this is you compile, right, and then you run test roadmap 3 for task 3. And if it passes, you should see test 3.1 passed. Okay, and then the second part of testing is to actually test the routes that your function returns. Okay, and you need to implement the function in navigator.c. Okay, so navigate. So at the moment, it just returns an empty route. Okay, but the way you test your navigate function is you run autotest 3. Okay, so autotest 3 will take a look at all the files in, all the testing files in task 3. Okay, so in the task 3 directory, there are files, data files for testing. There are .map files, which contains information about the roadmap. Okay, and then there's .query files, which contain information about the route request, right? So where the start node is, where the end node is, and what the departure time is. Okay, so I'll just quickly show you one .map. Oops. Okay, so this is information about the road map.
Okay, and the format of the file is described here. Okay, so make sure to read through this. Okay, so that's the .map files, and then the .query files are much smaller, right? So they just contain, the start node, the end node, and the departure time. Okay, and the .exp files, exp files, contain the expected results. Okay. So you don't need to worry about printing the route because the main program does this for you. Okay, so there's one more thing. So to help you out with calculating times, because that can be a little finicky, we've already provided a time.c module, okay, that you can use. Okay, so we have a couple of functions here. The first one is just a function to create a time struct. Okay, time new, takes in an hour and a minute. We also have a function for adding times. So the function takes in a time and a number of minutes, and it returns a new time, which is the result of adding the number of minutes to the given time. Okay, we also have a function for calculating the difference between two times. Okay, so given a start time and an end time, what is the duration between these times? And then we have a function for checking if two times are equal. Okay, so feel free to use these functions. You don't need to try to implement them yourself. Yeah, and here's their implementation. Okay. Yeah, so any questions about task 3? Okay, so task 4 is similar to task 3. So you're also calculating a route from a starting node and a finishing node. But in task 4, roads can be affected, can be closed at certain times. Okay, closed because of storms. Okay, so if a road is closed during a particular period of the day, then you can't drive on the road between these times. Okay, so for example, if a road is closed from 15:20 to 3:20 p.m. to 3:40 p.m., then that means no cars can drive on the road between these times. Okay, so if you want to drive down the road, you have to start driving. Since it takes 15 minutes to drive down, that means you need to start driving at 3:05, right? And otherwise, if you get to node 1 or node 2 later and you want to drive down the road, you can't. You have to wait until 15:40. Okay. Yep, so that's the whole idea. So roads can be closed at certain times. And in order to handle the road closures, there's a function in roadmap.c for adding a road closure. Okay, so the point of this function is to just specify that this road between node 1 and node 2 should be closed from this time, closed from, until, closed until. Okay. And in order to actually implement this function, you might need to add, you might need to modify some of your existing roadmap functions, right? So back when we were talking about task 1, I showed you the road struct in roadmap.h. Right, so we have a couple of extra fields that are used in task 4. Okay, so we have a Boolean affected by storms. So if the road is closed at a certain period of time during the day, then this field should be true. Okay. And if this field is true, then these two fields should also be set appropriately. So when is the road closed, and when does it open again? Okay, and the roads are closed at the same time each day. Okay, so that's it for the roadmap. And then you need to implement advanced navigate, right, which is just a function that calculates a route but takes these road closures into account. Okay. Cool. And there is an there is an additional challenge to this task, right? Which is that because of these road closures, sometimes it is actually more optimal if you actually depart from your starting node later than specified, right? So let's say you actually want to depart. The specified departure time is 12 o'clock, right? But if you departed at 12 o'clock, that means you'd have to wait for a road to be open, right? Let's say you might have to wait like 20 minutes or something, right? Then like it would be more optimal to depart later, right? So that you don't have to wait for the road to be open again, right? So part of this advanced navigate function is to make sure that you calculate the route that arrives the earliest, but also departs the latest possible, okay? So that you don't have to wait as long for roads to open. Okay, so yeah, that's task 4, and here's an example for task 4, which you can read through. Okay, and in order to test task 4, there are a couple of test functions for the roadmap, right? Because you needed to implement the add road closure function. Whoops. Okay, so we have 2 test functions in the roadmap for the roadmap. Just to make sure that your get roads from function and get roads to function stores information about road closures. Okay. Cool. So anyone have any questions about task 4? Yeah.
For the road closed, if I went on the road at like 3:19, it's still okay, right? It just can't be between those 3 times.
Are you referring to this road here?
Yeah.
Yeah.
Like if it was like, let's say onto that road at 3:19, it would still be okay, right? And or is it you have to consider extra time that takes to
Yeah, so you have to take into account the amount of time it takes to drive down the road. So if you decide to start driving at 3:05, that's okay, because by the time you get to the other end, it'll be 3:20, and that's when the road is closed. So you can start driving at 3:05, but if you want to start driving at 3:06, then you can't.
right? Because the road will be closed while you're driving down.
Oh, okay, so we have to.
Yeah. Okay. Any other questions? Okay, so I'll just show you running the order test command. So to test task 3 and task 4, you run order test 3 and order test 4. Okay, so here's the output from order test 3. Right, it's going to say test failed because we haven't implemented it. And order test 4. Okay, so both order test 3 and order test 4 will also run the test in test roadmap. Okay. So yeah, you don't actually need to run test roadmap. The program test roadmap, you can just run order test. But if you want to debug, it might be helpful to just run test roadmap. And you can also test your navigate functions manually with the test navigator program. Okay, so all order test does is just runs test navigator, right? And then it compares the output. But if you're debugging, then you probably want to run test navigator. Okay, so the rest of the spec is just FAQ. Yep, so have a read through this before asking any questions in the forum. Submission. Okay, and assessment. So just the last part. So task 1 and task 2 are worth 20% each. Task 3 is worth 25%, and task 4 is 15%. Okay. So like with assignment 1, there are time limits for assignment 2. So it's 3 seconds. Okay, and the time limits have 2 purposes, right? The first one is to make sure that your functions in task 1 and task 2 have the specified time complexity. Okay, so we're going to we're going to make sure that your functions here are O1. But they're also to make sure that your program doesn't have an infinite loop, right? So in task 3 and task 4, we actually won't be testing with a large amount of data. So we won't be testing with large roadmaps, okay? So the point of the time limit in task 3 and task 4 is just to make sure that your program just doesn't take forever because of an infinite loop. Okay, there's actually like no time complexity requirement in task 3 or task 4. Okay, and the rest of the marking, so it's the same as what you've seen in assignment 1. So we have memory errors and memory leak checking, and there's style marking. Okay, so that should be all for assignment 2. So does anyone have any other questions? Okay, so if not, we'll take let's say we'll take an 8-minute break, and we'll come back at 10:05, and we'll talk about the last part of graphs, which is minimum spanning trees.
Okay, so we're back. Okay, so what we're going to talk about now is minimum spanning trees. Okay, just the last subtopic of graphs shouldn't take us the whole hour, so there'll be time for questions at the end. Okay, but let's get into it. So, we talked about the idea of a spanning tree in the introduction lecture for graphs. So a spanning tree of a graph, and we're talking about undirected graphs here. Okay, so a spanning tree of an undirected graph is a subgraph that contains all the vertices of the graph, and it's connected and it doesn't have any cycles. Okay, and a minimum spanning tree is just the spanning tree, or a spanning tree that has the minimum total edge weight. Okay, so here is an example of a spanning tree and a minimum spanning tree. Okay, so we have a graph here with 5 vertices. Okay, and here is a spanning tree. Okay, so if you add up the edge weights, then you'll get 11, right? 6 plus 2 plus 2 plus 1, 11. And that's a spanning tree, but it's not the minimum spanning tree, right? So the minimum spanning tree would be these 4 edges here, right? So the total cost of these 4 edges is 9, right? 4 plus 2 plus 2 plus 1. And that's 9. Okay, so the minimum spanning tree is also a spanning tree, right? Just to be clear, but it's the spanning tree that costs the least out of all the spanning trees. Okay, and some applications are electrical grids and networks, right? So when you're building an electrical grid, right, to distribute electricity, well, how do you build an electrical grid? You need materials, right? You need wires, right? Mainly you need wires in order to connect nodes together, right? And these wires, they cost money, right? So you want to build your grid in such a way that you use as little wire as possible, so that it costs as little as possible. Okay, and in order to find the minimum spanning tree of a graph, there are 2 main algorithms. Okay, so there's Kruskal's algorithm and Prim's algorithm. Okay, so let's start by talking about Kruskal's algorithm. Okay, Kruskal's algorithm, invented by American Joseph Kruskal. Okay, so Kruskal's algorithm, I think, is fairly intuitive. Okay, so the way it works is, given a graph, we're going to create a graph that has the same number of vertices, but doesn't have any edges. Okay, so if the given graph has 5 vertices, we're going to create a new graph with 5 vertices, but doesn't have any edges. And then we're going to take the edges of the original graph, okay, and sort them in increasing order. Okay, so we're going to sort the edges of the original graph in increasing order. That means the weights with the smallest, the edges with the smallest weight will be first, and the edges with the largest weight will be last. And we're going to go through these edges, right, in increasing order. And for each edge, we're going to add the edge to our new graph if it doesn't create a cycle. Okay, so why don't we add an edge if it creates a cycle? Because then it wouldn't be a spanning tree anymore. Okay, remember, a spanning tree doesn't have any cycles. Okay, and we just keep doing this. So we go down the list of edges and we keep adding edges while they don't create a cycle
until we have a spanning tree. Okay, and the way we know whether we have a spanning tree yet or not is if v minus 1 edges have been added. Okay, that's because if a graph has v vertices, then its spanning tree has v minus 1 edges. Okay, we can show an example of that here, right? The graph has 5 vertices and the spanning trees have 4 edges. Okay. Okay, and in order to analyze Koskel's algorithm, there are 2 critical parts to it, right, which cost the most. Right? First of all, there is the problem of actually iterating over the edges in order. Right? So how do we actually sort the edges so that we can check them in increasing order? And how do we check if adding an edge would create a cycle? Okay, because that might involve some kind of graph traversal. Okay, so let's go through an example of Koskel's algorithm. Okay, so here's our graph. And can someone tell me what is the first edge that we would add to this? Yeah, so it would be 0, 1, right? Because we're adding the edges in increasing order, as long as they don't create a cycle. So 0, 1 is going to be our first edge. What's our second edge going to be? Yep, so it's going to be 3 to 4. Okay, so this edge does not create a cycle. What is the next edge? Yep, 0, 3. Okay, so at each point we're going to check if it creates a cycle or not. Okay, and what's the next edge that we add?
3 to 2.
Yes, so 3 to 2. Right, so actually, before we add 3 to 2, we're going to check 0, 4, right? Because 0, 4 is the next cheapest edge. But if we add this edge, it's going to create a cycle, right? So we don't add the edge. Now we check 1, 4, right? Adding that edge would also create a cycle, so we don't add the edge. And finally, we consider 3, 2. Okay, so 3, 2 doesn't create a cycle, so we add it. Okay, so 0, 4 creates a cycle, 1, 4 creates a cycle, and 2, 3 doesn't create a cycle. Okay. And now we're done because we have 4 edges. Okay. Cool, and here's a summary of the whole thing. Okay, so fairly straightforward in how it works. And here's the pseudocode. Okay, so we have 2 versions of the pseudocode, right? So they both work, but the way they check whether adding an edge would create a cycle differs. Okay, so here's the first version. We're going to create a graph, empty graph with v vertices. Then we're going to sort the edges. Okay, so how do we sort the edges? Maybe you use a sorting algorithm, right, to sort the edges. Right, maybe you use merge sort, right, which would be n log n, right? Or if the number of edges is e, then it would be e log e. Okay, so yeah, we sort the edges, and then for each of the edges in the array of edges, we're going to add the edge to the minimum spanning tree. Okay, and if the minimum spanning tree now has a cycle, then we remove the edge from the minimum spanning tree. Okay, so here we're not really checking if adding the edge would create a cycle. We're actually just adding the edge and then checking if there is a cycle. But I mean, the effect is the same, right? Okay, and after we add the edge, if the minimum spanning tree now has v minus 1 edges, then we return it. Okay. And after the loop, if we do end up outside of the loop at the end, then that means there is no minimum spanning tree, right? Because we've gone through all the edges, and we still don't have v minus 1 edges. Okay, and here's the second version. So as I said, the only way that these two differ is how they check whether adding an edge would create a cycle. Okay, so this one checks for cycles by checking if there is a path between v and w. Right, so for each edge that we consider, we're first going to check if there is a path between v and w. Okay, so between the two endpoints of the edge. And if there is already a path between v and w, before we add the edge, then we know that adding an edge, adding the edge would create a cycle, right? Does that make sense? So if there's already a path between v and w, right, then if we add the edge vw, it's going to create a cycle, right? So we only add the edge if there is not a path between v and w. Okay, so if there's no path between v and w in our new graph, then we add the edge. Okay, and that's the difference. Okay. In terms of time complexity, the time complexity should be roughly the same, right? Because both checking if there's a cycle and checking if there's a path involve a graph traversal, right? If you're using, if you're not using fancy data structures that we haven't covered yet. Okay, so in order to prove that the algorithm works, we can use a technique called exchange arguments, but proofs aren't required knowledge in the course, right? So this is just some extra details if you're interested. Okay, so the idea of exchange argument is we're going to take our algorithm, Kruskal's algorithm, and we're going to take another algorithm which supposedly chooses a different set of edges, right? And then we're going to prove that by gradually swapping the edges that the other algorithm chooses with the edges that our algorithm chooses, that Kruskal's algorithm chooses, the cost of the minimum spanning tree, so the total weight of the edges, never increases, right? So it always either stays the same or decreases. And we gradually transform the graph produced by the other algorithm, the spanning tree produced by the other algorithm, to the spanning tree that Kruskal's algorithm produces, right? And that proves that the tree that Kruskal's algorithm produces is optimal. Okay, so if you're curious, you can have a read through this proof outline. But it's quite interesting, the exchange argument. And if you go on and take COMP2521, which is algorithm design, you'll be required to make these kinds of arguments or proofs, right? So yeah, you'll get very familiar with this kind of proof structure. Okay. Okay, but of course, not required for this course. Okay, and now for the time complexity of Kruskal's algorithm. Okay, so we said that there were two critical operations in Kruskal's algorithm. There's sorting the edges, right? And then there is checking if adding an edge would form a cycle.
So sorting the edges, assuming you use your best sorting algorithm, would take E log E time. Okay. And then after we sort all the edges, we need to loop over all of the edges, which means the main loop has E iterations. Okay, and to check if adding an edge would create a cycle, we either added the edge and then checked if there's a cycle, or we checked if there is no path, right, between the endpoints of the edge. So if we do a BFS or a DFS to check that, then that would take O of V time, okay, in the worst case. So in the BFS and DFS lecture, we said that the time complexity of a BFS or DFS was big O of V plus E, right? That was the time complexity. Now here, the time complexity actually gets simplified to big O of V, okay? And the reason is that our minimum spanning tree will never contain more than V edges, right? Because we keep adding edges to the minimum spanning tree until it has V minus 1 edges, right? So that means the number of edges is actually smaller than V, right? And that means V plus E is less than 2 times V, right? So V of E simplifies to big O of V here. Okay, so cycle path checking is big O of V. And we're performing this cycle or path checking E times at most. So that means the total time complexity is E log E plus E times V, right? E log E for the sorting, and then E times V. Okay, and that simplifies to E, big O of E times V. Okay, and that's because log E is smaller than V. Okay, so reason why log E is smaller than V, let me just quickly explain that. Okay, so that's because okay, so first of all, we know that E is smaller than V squared, right? So that means log E is smaller than log of V squared. And because of log laws, okay, we know that log of V squared is 2 times log V, okay? Right, when you have a log of something to the power of something else, you can bring the power down outside of the log, so it becomes 2 times log V, and we know that 2 times log V is less than 2 times V, because log V is smaller than V, and that is, and 2 times V is just equal to, whoops, not log V, but OV, okay. So that's where the simplification comes from. Okay, so that's one way of checking if an edge would create a cycle. It's an inefficient way. The more efficient way would be to use a really cool data structure called union find. This data structure is kind of out of the scope of the course, but it is very cool. So it turns out that if you use the union find data structure, checking if an edge would form a cycle is close to O1 in the worst case. Okay, so it's not exactly O1, like technically, but it's a time complexity which relies on something called the inverse Ackermann function, right? So the Ackermann function is a function that grows really, really quickly. You can look it up online. And therefore, the inverse Ackermann function is a function that grows really, really slowly. And it's so slow that it could be considered effectively constant, right, O1. So that means the overall cost of Kruskal's algorithm ends up being E log E for the sorting plus E. Okay, so since you're doing this O1 check E times at most. Okay, and that means the time complexity simplifies to E log E, which is also equal to E log V. Okay, so once again, the log E here is equivalent to log V because of log laws, right? Because log E is equal to log, because E is smaller than V squared, right, which is 2 times log V by log laws, which is O of. Okay, so that's Kruskal's algorithm. Does anyone have any questions? Yeah.
What if, will there be a case where, let's say you have 2 weights that are the same weight, but picking one of them will result in a smaller spanning tree? And is this algorithm, does it check for that?
If you have 2 edges with the same weight,
Yes, but picking one of them will make the minimum spanning tree, and the other will be not minimum.
okay, so if you have 2 edges with the same weight, then it's possible that you might end up with 2 different minimum spanning trees, but they will both be minimal. So they'll both have the same total weight. Yeah. Yeah, so the spanning tree you get, I guess, depends on the sorting, right, and the stability of your sort. So depends on if you have multiple edges with the same weight, which one comes first, and that would affect the spanning tree that you get. Yeah, but they'll both be minimal. Okay. Okay, so the second algorithm that we want to talk about is Prim's algorithm. Okay, so named after Robert Prim, but it wasn't actually developed by Prim. It was developed by this guy, Yannick, way earlier. And the way it works is, again, we start off with an empty graph, but instead of sorting the edges, we're going to choose a vertex to start at and add it to the minimum spanning tree. Okay, so by adding it to the minimum spanning tree, I mean we say mark it as visited, right? We mark that vertex as visited or added. And then what we're going to do is we're going to look at all the edges between this starting vertex and all the vertices connected to it. So all of those vertices haven't been added to the minimum spanning tree yet, right? And I'm going to pick the cheapest edge out of those and add it to the minimum spanning tree. Okay, and then, so we're going to add that edge and the vertex on the other end to our minimum spanning tree, and we're going to repeat this process. So at every iteration, we're going to look at all the edges connecting a vertex in the minimum spanning tree to a vertex that's not in the minimum spanning tree. Okay, and we're going to choose the cheapest out of those edges and add it. Okay, and we just keep doing that until we have v-1 edges in our minimum spanning tree. So to clarify that, let's look at an example. Okay, so here's our graph, and suppose we choose to start at vertex 0. Okay, so we'll see that the order in which we add edges here is not going to be the same as Kruskal's algorithm, right? Because we're following a different algorithm. But the first edge that we add here is going to be 0, 1. Okay, so it's going to be the same as Kruskal's algorithm, but it'll soon be different. So we're going to add Yeah, so we're going to consider these three edges, right? Because these three edges connect a vertex that's in the minimum spanning tree to a vertex that isn't. And the cheapest edge out of these three is 0, 1. So we're going to add this edge. Okay, so now what edge do you think we're going to add next? Yep, so it's going to be 0, 3. Okay, so in the next iteration, we are considering these four edges, okay, because they connect a vertex in the minimum spanning tree, which are 0 and 1, to a vertex that's not in the minimum spanning tree. And the cheapest edge out of those is 0, 3. So we add 0, 3. Okay, what edge are we going to add next? Yep, so 3, 4. Okay, so in the next iteration, we consider these edges. Okay, and the cheapest edge out of those is 3, 4. So we add. And finally, we consider these three edges. Okay, and the cheapest edge out of those is 3, 2. Okay, and now we're done. Okay. Okay, so here is the pseudocode. Now the pseudocode for Prim's algorithm here is a little more abstract. So, okay, the way you implement it might actually be quite different from how it's expressed here. But I'll just go through how this pseudocode has written it. So we start off with an empty graph with v vertices, just like with Kroskel's algorithm. Then we create a set containing all the vertices that are in the minimum spanning tree. Okay, so here we just pick vertex 0 and add that to our minimum spanning tree. Now the way you would implement this might be a Boolean array, right? A Boolean array of size v, where all the entries are false at the start, right? And then to mark vertex 0 as being in the minimum spanning tree, you would just set the first array element to true. Okay, that's how you might do it. Then we have an unused edges set. Okay, so just a set containing all the edges that we haven't added to the minimum spanning tree yet. Okay, and while we haven't added all the vertices to our minimum spanning tree, so while the size of this used v set is smaller than v, we'll go through our unused edges set and find the cheapest one that connects a vertex in the minimum spanning tree to a vertex that isn't in the minimum spanning tree. Okay, so that's what this is describing. Okay, so so we find an edge, the cheapest edge, such that S is in used V and T is not in used V. Okay, then we add that edge to the minimum spanning tree. We also add T to the set of used vertices. So we essentially add that vertex to our minimum spanning tree. And then we remove the edge from our set of unused edges. Okay, and finally we return the minimum spanning tree. Okay, so I said that this pseudocode is not, might not be the way you actually implement it. Right? And what I mean is that you might not actually use a set of unused edges, okay, because that is a little inefficient. right? But what you might use instead is something like a priority queue, right? So while you're adding the vertices to your minimum spanning tree, you also add the edges connected to those vertices into the priority queue, right? And then at each iteration, you remove one of these edges from the priority queue, right? And if it satisfies this condition, where one of the endpoints is in the spanning tree and the other endpoint isn't, then you add that edge to your minimum spanning tree. Okay, so that's how you might use a priority queue. Okay, so what's the time complexity? So first of all, our algorithm needs to consider all of the edges of the graph, all right, in the worst case. So this is going to contribute to O of E in our time complexity. Okay, and our loop here in our pseudocode has V iterations. Okay. Because every iteration we are adding one edge and one vertex. Okay, so technically it might have V minus 1 iterations, but V minus 1 and V, that doesn't change the time complexity, right? Okay, and then in each iteration, we need to go through our set of unused edges to find the cheapest one that satisfies this condition. Okay, so if we just implement the set of unused edges as, say, an array, then this would cost O of E time, okay, in order to iterate over all the edges and choose the cheapest one. Okay, so that would make the overall cost of the algorithm O of E for considering E edges at most plus V times E, okay, which is big O of V times E. Okay, pretty costly. But another way of implementing it is to use another fancy data structure called a Fibonacci heap. Okay, so Fibonacci heap, so if you use a Fibonacci heap, the cost of finding the minimum weight edge is log E, okay, which is equal to log V because of the log laws that I talked about earlier. And that means the overall cost of the algorithm would be E plus V log V. Okay. So that's Prim's algorithm. So does anyone have any questions about Prim's? Okay. So we have two algorithms, Kruskal's algorithm and Prim's algorithm. So which one is better? Right, so it turns out it depends on the graph. Okay, so first of all, Kruskal's algorithm is we're assuming their most optimal implementation here. Okay, so Kruskal's algorithm is E times log V, and Prim's algorithm is E plus V log V. Okay, so what we're going to do is think about what happens when the graph is sparse and if the graph is dense. All right, so first, let's think about what happens when the graph is dense if the number of edges is close to V squared. Okay, so if that's the case, then Kruskal's algorithm would be V squared times log V. Yep, because E here would be close to V squared, and Prim's algorithm would be V squared plus V log V. Okay, so v squared plus v log v is better than v squared times log v, right? Does that make sense? Yep, so v squared plus v log v, that simplifies down to v squared, right? With Kruskal's algorithm, we have v squared times log v. We can't simplify that. So Prim's algorithm would perform better, right, on dense graphs. Okay, what happens if the graph is sparse? All right, so the number of edges is closer to v. Okay, then that means Kruskal's algorithm is going to be O of v log v. And Prim's algorithm, since E here is closer to v, the time complexity would be v plus v log v, which simplifies to v log v. Okay, so if the graph is sparse, then both Kruskal's algorithm and Prim's algorithm are O of v log v. Okay, so now which one is better depends on the implementation details, right? So what data structures do these algorithms use? So Kruskal's algorithm, if we use the union find data structure that I mentioned here, the union find data structure is an array-based data structure. Okay, so it's out of the scope of the course, but just so you know, it's an array-based data structure. And in general, array-based data structures perform better than linked list data structures, okay, which is what Prim's algorithm uses. Okay, so all else considered equal, array-based data structures are more efficient than linked data structures. So Kruskal's algorithm would actually perform better on sparse graphs. Okay. Cool, so there are some other minimum spanning tree algorithms, which we're not going to cover, but for your curiosity, there's an algorithm called Borufka's algorithm. And there is a very interesting algorithm by Kaga, Klein, and Tajan. I don't know if that's how you pronounce the names, but the time complexity of their algorithm is big O of E on average, which is very impressive. Yeah, but it's also non-deterministic, which means it's a randomized algorithm. It uses randomization. Okay, so if you're interested, you could have a look at that. Okay, but that is the end of minimum spanning trees, and that's also the end of our graphs topic. Okay, so next week we're going to talk about another data structure called hash tables. So you might have heard of that. And then in week 9, we're going to talk about priority queues, which we've already mentioned a couple of times in our graphs lectures. And finally, we'll cover a special data structure called tries. Okay, but that's all for today. So I'll see you all next week.